Okay, right. So thanks for being here. So this will be the last lecture in my series on GHD and on Soliton gas theory. So last time I introduced two different but complementary interpretation of what a Soliton gas can be. Okay? And depending on what I will be doing, one of the two interpretations might be better than the other. So I'll start this lecture by a quick recap of the last one to reintroduce the concepts, and I'll jump from one interpretation to the other during the lecture. And then I'll build on this to construct the hydrodynamics, so the large-scale dynamics of the KDV Soliton gas. So again, this time I will be mostly focusing on the KDV equation. So it's integrable nonlinear dispersive PDE that you can see here, and it's integrable in many respects. So it's solvable via inverse scattering transform. It has a zero-curvature representation, a lag spare, it's bi-Hamiltonian, etc., etc. And all of this also implies that it admits an infinite set of conserved quantities. Okay, that I rewrite here for the sake of notation. So here, and the time conserved quantities that I will also refer to as charges from time to time, I write Q, and the space and the currents I J. And because of those quantities are conserved, the density of charges and the density of currents are related by this identity, this conservation equation. And these are the microscopic conservation laws of my model, which I will use to build the hydrodynamics of the Soliton gas later. Okay. And on top of that, KDV also admits n Soliton solution, which are Soliton solutions that asymptotically will decompose into trains of well-separated solitons like that. And all of these solitons are indexed by two parameters. Okay, so the first one is the spectral parameter eta, which represents the amplitude and velocity of the soliton, and its impact parameter x plus minus here, which represent what position the soliton would have if it did not interact with the others at t equals 0. So those two, those set of two parameters, set of n couples of parameters eta and x are sufficient to reconstruct the solution at all times. They play the role of action on the variables here. Okay, right. So last time I introduced the notion of Soliton gas through a toy model that was discussed first by Zaroff in 1931, which is called the rarefied Soliton gas. It corresponds to a random solution of the KDV equation, but one that can almost everywhere in time be approximated as a train of well-separated solitons. So as I said earlier, normally this is only an asymptotic, this approximation is only valid asymptotically, but here I put myself in a regime where it's valid at all time. Okay. And the randomness comes from the etas and the x.
But it is just an ansatz, it is not a...
No, it's
possible to get it as a solution of the KDV with random parameters.
Yes, it is possible. But so it's a very peculiar case. And, here it's mostly a toy model. So of course you can pick a time at which this is not true, but you say that almost everywhere in time this is. Okay, so yeah, and the Soliton gas, the rarefied Soliton gas, is the limit of this n goes to infinity with a given joint distribution of eta and x. Okay. So, and this is roughly what it looks like. So this is not quite rarefied, as you can see. At some point in time, this approximation breaks, but roughly.
Sorry,
yeah. Right.
I mean, what do you mean by random? So you have the eta I and the xi which are random.
Yes.
So you take them random from some distribution,
right.
And then you can check the linear solution of your equation.
Yes.
linearization?
for linearization.
But the Soliton, the x's have to be well separated.
Yeah, so it was separated.
So
It's
it's
the sum of the others.
that depends maybe on the probability distribution.
Yeah, exactly. So you,
So, I mean, there's some constraint on the probability
Yeah,
that you have
yes.
to use in order to.
so those constraints, I talked a bit about those last time. I'll mention quickly what are these constraints. Again. So that's roughly the basic object I'm going to talk about. And so the point is here I want to study the statistical properties of ensembles of rarefied gas to introduce the notion of gas. And to do so, the first thing I introduced last time was this spectral support gamma. And this is a collection of bands from which the etas can take values. And I do that because, as I told you during my second lecture, you can associate a solution of the KdV equation to a particular bound gap spectrum of the associated last operator. Okay. So here I'm dealing with a Soliton gas, so we should expect that the spectrum should be a collection of discrete points. But ultimately, I would want to use this kind of Soliton gas formalism to build a more general solution of KdV, to approximate a more general solution of KdV.
There would be bound states in the corresponding Schrödinger equation. There would be a lot.
Not in KdV.
Use them.
Not in KdV. There are no bound states in KdV.
No, but you have a scattering potential.
Right.
Just take a potential. There would be bound, the bound states. They produce electrons.
I don't think I understand.
No, but there is continuous spectrum.
Yes, exactly. But that's my point, in fact. Because
Continuous spectrum solution of continuous spectrum, they are different.
yeah, they are different. But what I will argue is that you can approximate a solution with continuous spectrum by taking a band and populating it densely with points of discrete spectrum.
Actually, you can get bounds on this approximation.
Isn't it if
yes.
you have the bands, you cannot have bound states if you already impose this band structure.
No, there is no bands.
There is, this is what he imposed.
So okay, so this is not the spectrum.
These
This is not the spectrum. This is a spectral support from which the etas can take values. And when
Which describes a physical initial configuration.
yeah, and then this at some point in the lecture I will also identify with the spectrum of certain n-phase solution. Those n-phase solution I can approximate using Soliton by populating the bands accordingly. Okay. And yes, indeed, there are also bounds for this approximation. So there's a paper by Tobbis and Jenkins, that's very recent on that.
And what is xi?
So the xi's, so here I call them the impact parameters. They are the position of the Soliton at time equal 0 if they don't interact. Okay, so you assume that if this kind of approximation were true at all times, that if the Solitons were free, that's where they would be. Okay. So in practice, the interface sheet and finite time, the position is not quite that, but you can use this as a parameter to reconstruct your solution using the power function for the polar introduced. Okay. Other questions?
So,
right.
This approximation you use as for initial data that decays and the periodic or quasi-periodic.
Yeah.
Okay. Not necessarily just, everything is determined in KdV by the initial conditions.
Yes.
Each function you take solitons and plus continuous.
Yes.
If it is periodic or quasi-periodic, you have only band spectra,
Right.
no bound states. But nevertheless, you approximate by a solution which somehow mimics bound states.
Yes. Yeah, indeed. And so at this point, this is the rarefied gas. So it's a particular case of Soliton gas, but I also introduce a more general dense gas later. Okay. All right. So the main object I will use to characterize my Soliton gas and its two properties is what I call the spectral density of states, rho. Here. And here I introduce it as a way to count the number of solitons in the vicinity of the space point X with spectral parameters in the vicinity of eta. So it's the density of solitons both in real and in spectral space. Okay. So
And it's just you.
yeah. It's in your
input parameter.
exactly.
That's functional parameter.
Exactly. It's
Joint distribution of
right.
parameters.
Yeah. And it corresponds to the joint force distribution of the xi. You can write it in terms of the xi as well.
Why it depends on T.
So yeah, because then you
Because eta and the X is a new dependent.
no, that's true. But at that point here, this is homogeneous, but then I can consider slow modulations. All right. All right. And the last thing I can introduce also is the so-called spectral flux density, which counts the number of solitons that are passing through a point X with parameters in the vicinity of eta, in the vicinity of empty. Okay. Right. So those two objects are what I need to describe the statistical properties of my gas, and now I want also to have a way to characterize the large-scale dynamics. If I put some motivation, I want to describe the hydrodynamics of my gas. And since the interaction between the solitons are elastic, so the etas can change programmatically isospectral, that means that the density of state can only be transported. So I can write this identity between the density of state and the spectral flux density. And now what I need to do is find a way to relate F to rho. And last time I told you that by definition, the F should just be rho times the velocity of the soliton moving at the velocity of the soliton with spectral parameter eta. But in fact, this is not quite the BEV velocity of the soliton, because in the rarefied gas, the soliton will only move with its BEV velocity until it collides with another one, in which case it will incur some scattering shift, some position shift. Okay. And since here in the rarefied gas, the gas is really diluted, collision almost surely don't involve more than two solitons at a time. Okay? So that I can write that approximately the effective average velocity of the solitons over large periods of time and large distances is athletic order of its velocity, but it's modified by all the position shift it occurs. So here this is the position shift and this is a collision rate. To illustrate this, here's a small figure where you can see the propagation of a trial soliton through a rarefied gas. And as you can see, here its effective velocity is a bit bigger than its velocity. Okay. So that's kind of the objects I'm describing here. And of course, for these objects to make sense, the variations must occur over scales that are much larger than the scales associated with the variation of KDV wave field, U. Okay? So these equations, they describes the variation of the statistical properties of the gas over macroscopic scales. They are essentially the Euler hydrodynamic equations for solid gas. And now today I want to find a way to derive the same kind of equation, but for dense gas. Because for a dense gas, things become a bit more complicated. So this is an example of a 150-second solution. And in this case, in dense gas, solitons are constantly overlapping and interacting with one another. So if you think about the effective velocity, for example, given that it's not clear that it should only involve the two bodies separation. Okay. And on top of that, also, if you look at, if you think about the density of states, here, since solitons are overlapping and interacting in nonlinear ways, they're essentially big localized, so you cannot recount the solitons here. But what we do know, however, is that if you take a piece of this gas, a fluid cell, and you are isolated from the gas like that, well, you know that up to a small radiative correction, if you let it evolve asymptotically, it will decompose into a train of well-separated solitons. And then you can count the solitons, then you can measure the position and the amplitude to get the threshold impact parameter with which you can reconstruct the solution profile. Okay. Yes.
How do these solitons interact?
Oh, okay. So they have a period where they overlap, they interact in a fairly completely elliptic way, very nonlinear. But asymptotically, the resulting effect is just a position shift. So while they're interacting, it's a bit complicated, but once they've interacted, the resulting effect is just a position shift.
But I can see that in your equation.
Can you see that?
The interaction.
It's pretty implicit. It's what do you mean?
So it's not like a force.
No, it's not exactly a force. So if I show
It's
you,
not a superposition.
no, the superposition doesn't work. So it works only asymptotically when they are separated. Otherwise, it's.
But can you tune the interaction?
Yes, you can. So typically, you write KdV in its dimensionless form like that. But if you rescale the amplitude by a parameter, what it does is put some parameter in it. This changes the nonlinearity, so the interaction between solitons. All right. Okay, so here's an illustration I showed last time, but I'll show it again today. So if I start with this Gaussian initial condition, for example, a priori you cannot tell me how many solitons there are here, or where they are exactly, or what the threshold parameters is. But if I let it evolve, KdV for this, then solitons separate, then you can identify the elements there. So as you can see here, the interaction can be a bit complicated, so you can reconstruct. Right. So here in the dense gas, the meaning of the density of states it counts the number of solitons that would asymptotically emerge from some window of space with parameters in the vicinity of each cell. Okay, and based on this asymptotic approximation, we can say that asymptotically, solitons essentially they behave as free particles that move with velocity for eta square. And last time I used this analogy to construct the thermodynamics of the Soliton gas, so the statistical mechanics picture of the Soliton gas. But last time the third part lied in how to relate these asymptotic parameters, the xi, to the properties of the fluid cell at time t equals 0. Okay? As I said, these are the position of the Soliton if they interact. But in practice, they cannot be between 0 and L. They cannot be in the fluid cell because the solitons interact and they shift. So last time I proposed a heuristic argument to relate these parameters to the size of my initial fluid cell. I won't go over it today again, but in a way you can assume that you can treat solitons as point particles that are instantaneously jump when they collide. So here it's based on the fact that you assume that you can carry out a reasoning that are similar to what we did for the rarefied gas, but also for dense gas. And so that's not rigorous, of course, because solitons they localize, they don't interact instantaneously. But we have reason to think it works, and that's something I argued last time, and we'll argue a bit more today as well. Okay. So if you ask yourself where your impact parameters should be given the position of your initial fluid cell, so in order for your solitons to initially be in your fluid cell, then so you can ask yourself what are the conditions on the impact parameter in order for the solitons to be in the fluid cell initially, and you can write a relation like that describes a change of metric between the asymptotic coordinates and the finite time coordinates due to the scattering shift, the position shift, and the fluctuations. Okay, so here we introduce k as the asymptotic space density, okay? And it's completely determined by the spectral density of state. Yeah. Right. So from the previous heuristic arguments, last time we were able to construct the thermodynamics of the Soliton gas. Here I will quickly recall the main results. We were able to define a free energy density here, F, as such, and since K, here's the asymptotic space density, is uniquely determined by rho, then it also means that the equilibrium state here is completely determined by rho. Okay.
I'm sorry,
yes.
I'm not sure I understood. I understood the spirit,
yeah.
But so I'm a bit confused. So K is the asymptotic space,
right?
Yes. While rho is the one at finite time that we have.
Ah,
no.
okay.
I am sorry because I.
No, you're right. It's not quite that. So rho it essentially counts the soliton within a window, right? And K it characterizes this change of metric that allows you to express the impact parameters in terms of real space. So you say, okay, my solitons must be in this window of time equals 0. Where should be the impact parameters so that it is true?
Okay.
For the estimate.
Okay, thanks.
So K describes it.
Okay, thank
you. Okay. And so yeah, here the equilibrium state is completely determined by rho. And in fact, you can also relate rho to the Lagrange parameters of your GGE, so your inverse temperature, if you prefer, with some yang-yang like equation that I won't write here because
Why does the energy raise like that?
Why does it look like that?
What's the interpretation?
What the interpretation? Okay, so that's a good question.
If there is.
No, there's no. I don't have a clear interpretation why it looks like that. It's just results of the calculation. So
you derive.
yes. So that's one of the things I did last time. So that's
a good definition of free energy density in this context, because we know the definition of the Hydrodynamics. Not clear.
oh no, but okay. In this sense, it works exactly as a free energy of statistical mechanics. So you can write your partition function for your Soliton gas as exponential minus n times f. In this case, f.
And well, what is that? Z?
Z is the number of n Soliton solutions that are compatible with the constraints that your solution must be within.
Somehow it reminds me more of the Boltzmann definition of the entropy, not free energy, but
Yeah.
You can do gives
Yeah.
integration over all the operations with the weight.
Yeah, because on top of that, you're putting this weight,
just if you have number of something, and then the exponent is less than the of entropy, like in Boltzmann's case, what is entropy? Just e to the power entropy is the number of states in a given interval of energy.
But here you will have
If you have
this is indeed
an analog of energy.
So you have this contains the entropy, but it also contains the Gibbs weight, which are some detach m. So you're putting like you're doing in statistical mechanics, instead of putting exponential beta e, let's say, here since KdV has an infinite number of constant quantities, you're putting all of those constant quantities here.
If you define your partition function as the sum or configuration,
Yes.
Which configuration you will be dealing with?
All of those.
Yes.
Different. Yeah.
All the possible configuration in a given window.
Right. So you're summing your most windows are written, but you're looking at only the ones that are at equal 0 compatible to be given.
Would that be like an average over this order of eta I and xi?
Yeah. Yes. Sorry, that's things that I did last time, so I didn't want to spend too much time here. But maybe I should have started off. All right.
But
Right.
so this formula on the next slide,
Yes.
it's not the universal formula. It's not always like that.
It's not always like that. What do you mean?
I mean, if I take a quantum kinetic model.
Ah, no, of course. No, this works for the solution gas of KdV. Yeah, of course. And for example, also here, I'll take this opportunity also to introduce the occupation function, which in the case of the KdV solution gas plays the role of the density of free energy both in spectral and in space. But of course, if you have a Fermi equivalent of your free energy density, it takes a different form. Okay. So here, this is specific to the KdV solution gas. Okay. And here, so the name occupation function kind of makes sense, as you can see, that it's essentially the ratio of the density of states over the asymptotic space density, with the ratio of the density of solitons in spectral and in real space over asymptotic space densities. Essentially, you can see this as the density of solitons within the asymptotic space, okay? Within the impact parameters space. All right. So from this construction, last time I showed you how to derive the ensemble average of the charge densities. So there is this very intuitive form. It's just the integration of H, which is the amount of a charge Qn carried by a single soliton integrated over the density of states. And so you can get this by differentiating F with respect to the Lagrange parameters associated with the concept quantity question. And I also wrote the expression for the static covariance matrix, which is the integrated correlation function between the charges, and it takes also this rather compact formula that involves the dressing of the function h. And here, this dressing, so it's defined, the dress function is defined by solving some kind of Fredholm equation of this kind that involves the phase shift. Yeah. So this dressing operation is pretty important in GHD, and as you will see, many results can be written in terms of the dress quantities. Right. Yes.
In this, so in the analogy with GHD, what would the K function correspond to?
K would be rho S. So you have our P prime dress.
Okay.
Right.
So the density of available state.
Yes. Yeah. Exactly. All right. Okay. And yeah, in fact, that's almost the answer to the question. K, you can reframe it in terms of glass quantities. So this equation is very close to the one for K here. And you can write that K is just happiness to K, and the velocity of the solution is the square, so this is
okay. Okay.
Right. Okay, but there's also another way to look at this problem, right? That I mentioned last time, and it's through the lens of finite gap theory, which associates the n-phase solution of the KdV equation to a particular bound gap spectrum of the associated Laplace operator. Okay? So this approach is more rigorous, and it doesn't use any heuristic analogy between solutions and particles, but also it doesn't really lend itself to statistical mechanics interpretation. So that's why I said earlier that both were a bit complementary. So here I'll briefly recall the ingredients to characterize a Soliton gas through this formalism. I won't go into the details like I did last time, but it's just to fix the notations. Yes. I thought you were
No, so this P prime dressed.
Yes.
In relativistic and so even if I take the hyperbolic sign and
it's not relative.
so from like I don't know, leaving a TBA to work.
Yeah, it's closer to ways. Yeah. Okay, so for given n gap spectrum of the Laplace operator, you can write the associated n-phase multivariate solution of KdV in this form, which involves the second log derivative of the Riemann theta function. Yeah. So here lambda and phi are constants, and this P here is a so-called n-by-n Riemann Cleaver matrix. So all these objects, they depend non-trivially on the endpoints of the band. So I won't remind you how they do, but that's, we know how to compute them given the spectrum. But the most important object here is probably the phase vector theta here, because this is what encodes the x and time dependence of my n-phase solution. And they take this originally from kx plus model g plus theta naught. Okay, so they are really phases. And of course, here the choice of the initial phase is a theta 0 is free. But the choice of the wave numbers, the frequencies, the k's and the omegas is not. And they depend on the spectrum. And they depend on the spectrum and on each other through what are called the nonlinear dispersion relations that are written here. So this involves the Riemann Cleaver matrix, it involves the lambda constant, it involves also these vectors Cn and C-1 that also depend non-trivially on the spectrum. And these are the main objects as the basis of the construction of Soliton gas using this kind of formalism. That's what I will use to define the density of states and the spectral flux density. So here I'm going a bit fast because I went over that last time. But,
you mentioned that these are periodic solutions. Is it important? Because generically they are quasi-periodic.
Yeah, they are quasi-periodic. Yeah, that's true. No, that's true. It's
necessary to your approach?
No, it's quasi-periodic. It's just okay. So to get the Soliton gas, what you do is you take your n-phase solution and you take the subunit limit. So you take all of your bands and you shrink them to points. Okay. But if you do this, what you get is just an n-Soliton solution. So you don't get a Soliton gas. Overall, you will get something that is zero density over the whole line. And that's something you can see because when you shrink the bands, the wave number go to zero. So you have essentially zero wave density over the line. But to get a certain gas, as you are shrinking your band, as you are taking the certain limits, what you want to do is you want to increase the number of bands, okay, in order to keep these quantities constant.
But the number of gaps will increase.
It will increase.
Yes. The gaps will be more numerous.
Yes, exactly.
So it will be more and more.
So you start with this, and then you have the
Fractal spectrum.
Exactly. And you want to keep these quantities constant because k's are wave numbers, so this quantity has a natural interpretation in terms of average number of waves per unit length. And since omegas are frequencies, this can be interpreted as a flux. Okay. And okay. So now we can reevaluate the nonlinear dispersion relation under this thermodynamic spectral scaling. And now if I define my density of states like that, because I just told you that this has a natural interpretation in terms of the density of wave, here you see that rho is indeed the density of solitons per unit length and per spectral flux. And similarly, I can also introduce a spectral flux density so that it plays the same role for the frequencies and rho does for the wave numbers. Okay. And under this limit, my previous nonlinear dispersion relation becomes those two integral equations, where this new function sigma here is called the spectral scaling function. It encodes all the relevant information about the spectrum. To be more specific, it's so the precise band gap ratio around spectral point E. Okay. So the NDRs, they related the wave numbers and the frequencies to the spectrum. Here, in the thermodynamic case, they relate the density of state and spectral flux density to this band gap ratio. Okay. All right. And what's nice here is that you can also reinterpret those two NDRs as two examples of rest quantities. Okay, so you see that O and F, they solve a Freedom equation with and kinds that involve this centering shift. And in fact, yeah, the first one is just the definition of the asymptotic space density, and the second one corresponds to orbit acute rest. And this two identification, it also allows us to realize that sigma, in fact, is just the inverse of the occupation function I introduced. So again, I'm going a bit fast. That's something I discussed first. All right. So now basically, all I need to construct the hydrodynamics of my Soliton gas. It's something I wanted to do last time, but unfortunately I ran out of time, so I'll discuss it today. And then I'll talk a little bit about two particular cases of Soliton gases, so the polychromatic and the condensates. And that's in order to illustrate what I've been talking about today, and also motivate the use of this Soliton gas complex. Last time I told you that I would also talk about how to numerically generate and Soliton solution, but I won't have time to, so I abstract it. And then I'll briefly talk about potential extensions to GHD, either as a way to refine the description of the KT Soliton gas, or by highlighting some other integral models for which constructing the GHD may be not trivial, and that brings some interesting twist to the picture. Okay? All right. So, okay, so here with the density of states and the spectral flux density, I have everything I need to characterize statistical properties of my gas at equilibrium. But now I want to see how it evolves on large scales. And the first thing I need to look for is the effective velocity. So earlier when I talked about the rarefied gas, I told you that solitons within the gas don't exactly move at their velocity. The velocity is modified by the shift angle, and that should be even truer for dense gas, right? And earlier also I defined the effective velocity as the ratio of the spectral flux over the density of states. And now the nonlinear dispersion relation gives me a way to evaluate this. So as before, I define this effective velocity in this way, and this gives me an integral equation for the effective velocity to solve. And here, there are some interesting things here. So the first thing is that even though we are in the dense gas and solitons interact with several others at the time, here this expression only depends on the two-body scattering shift. Okay? So, and even more than that, this is phenomenologically what we would expect if we were dealing with Born particles that would instantaneously jump when they collide. So that kind of further justifies our heuristic approach we took earlier. So at least at very large scales, it seems to be correct. Okay. Right. So we can also easily recover the effective velocity for Zaharoff's Soliton gas by looking at this equation. You iterate once this integral equation, and then you take the limit of low spatial density. so that you neglect the global integral terms. Then you get very fine effective velocity. And this structure is very general when it comes to the effective velocity in many body interval systems. So we have written its most generic way, where here the only things that are model dependent are the group velocity and the phase shift price. And traditionally, the effective velocity is also written as a ratio of dress quantities. So you start with the usual expression for the group velocity as the ratio of the derivative of the energy over that of the momentum, and then it's natural to think that the effective velocity would be the ratio of E prime dressed over P prime dressed, and so that's not the only way to define it. Okay. And when it comes to KdV, here's the group velocity for eta squared. We also know that the momentum of KdV by convention will be chosen for eta squared as well. So E prime should go as eta cube, which means that the effective velocity should go as eta cube dressed and eta dressed. And this, using the identification from last slide, is exactly it. The ratio of the spectral flux over the density of states. So those two approaches are consistent this way. Okay. So now we have enough to construct the hydrodynamics of the KdV Soliton gas. So again, let me write my microscopic conservation laws here, as I did during my first lecture on hydrodynamics. And the difference here is that I'm dealing with an integrable system, so I have an infinite number of conservation laws of hydrodynamic time. And then I assume that I can perform a separation of scales, and I can work under the hydrodynamic approximations, the approximation that the average of observable at xt is roughly the observable average of that observable within a local GGE whose Lagrange parameters depend slowly on x and t. So again, I'm going fast here because I went over this procedure already a few times previously. So then I write my mesoscopic conservation laws by performing a fluid average. And now I can also use the results I got from my statistical mechanics approach. So I can write the average of charge densities in terms of the density of states, but now I'm considering slow modulations of my Soliton gas, so my density of states now depend on x and t. And similarly, I can express the average current density in this way, whereas this is again just a spectral flux. So at this point, those quantities are defined in a heuristic way, right? But I can also define them from the finite gap theory in the thermodynamic spectral limit, and they take the same point. Okay? And if I put all of this together, and if I use the fact that the set of the agents is complete, then I end up with this hydrodynamic equation for the density of states, where again, this time V has of course also been promoted to depend on x and t. Very straightforward. Okay. So this is the generalization of the Soliton gas equation I wrote for the rarefied gas, but this is generalized to dense. So essentially what changes is that you replace the bare velocity of the second scale by the effective velocity. So this is not just an expression, but it's an equation for V2. So again, this can be derived from finite gap, so I won't give you the details here, but it amounts to considering slow modulation of the endpoints of the bands, and then performing a multi-scale extension, and that's what you get adjoint order in the thermodynamic spectral limits I described earlier. Okay. So there's also yet another approach when it comes to deriving the effective velocity that I want to talk about, because I think it highlights some important features of this kind of hydrodynamic equations. And the alternative method I now want to talk about, it takes a more geometric approach, and it makes use of the change of metric I mentioned earlier. So asymptotically, solutions are free, they don't interact, they just move according to their velocity. So the density of states asymptotically should trivially follow a UV equation. But now I can perform the change of metric I mentioned earlier, and after some computation, what I get is this transport equation for the incubation function with V that takes the same form as before. And there are two important things here. So the first one is that the Soliton gas kinetic hydrodynamic equations, they are just equivalent to the UV equation under this change of metric to account for the scattering shifts and the dilution of space.
Is this equation related to, in some way, to the symptotic dynamics?
Yes, it's exactly that under this change of metric.
Why is it the case? I mean, the dynamics just describes non-interacting.
Yes, and you
so the change of variable kind of take into account the interaction.
Exactly. So what you say is okay, your particles are moving without interacting. So you have this non-interacting picture in mind, and then you say that every time your particles interact, there's a phase shift, so it dilutes the space. So you take into account the interaction in this way.
Yeah, sorry, I'm not sure. And what is a small n?
N is the occupation function, the filling fraction.
What is the relationship between n and rho?
Yes, the relation between n and rho is. Yeah, no, it's okay. It's here.
Ah, okay.
Right.
Okay, thanks.
So yeah, so indeed you see that yeah you get rho over k at some point, and that's right. Okay. And the other interesting thing here is this equation, this transport equation for the occupation function, but it's completely equivalent to the previous equation for the density of state rho, except this time the effective velocity is outside of the x derivative. So what we've done here is essentially we've diagonalized our system. Okay, so n, so the occupation function, or equivalently sigma, they play the role of a continuum of Riemann variance, like I introduced in my first lecture a while back now. Okay. So, okay. So given that we have a Riemann variant form for our GAG equation, we can also ask ourselves what else we can bring from the theory of hydrodynamic type systems that I introduced in the first lecture. So the first thing we can ask about is there some kind of property that is analogous to linear degeneracy? And in fact, yes, so we can write a continuous version of linear degeneracy property. And can use this to infer that there should be no shocks in GHD. In fact, that's something that's been derived by Ben and his student Friedrich recently through completely different methods. The other thing we can check is if there is something analogous to the semi-Hamiltonian property. And again, there is a continuous analogous, and this means that the generalized hydrodynamics equation should be integrable via holograph transform. And presumably this autograph transform in this case should look like that, where here G plays a role of functional degree of freedom. So if you know, for example, n at t equals 0, you can set t equals 0 in this equation, you can differentiate with respect to x, and this will give you G in terms of n at x equals 0, and then you can reconstruct your solution. So here I say it should presumably look like that because contrary to the linear degeneracy in property, it's not been checked properly that it would look like that. But we at this point we assume that it should carry over to the continuum limit as everything else. So this should be checked at some point. Okay, so this is where I originally planned to end lecture 3. So here are some references I used to prepare it. And maybe I think this is a good time for a break. We start again later talking about some specific examples of certain gases. Right.
The thing that you said that they are integrable using
Yes.
the transport is true only for the solids, for the KDV, or it's okay? I see.
So it doesn't depend on the initial three functions or whatever. Just the property of the equations. Linearized, whatever.
Yes. There may be also pathology.
Yeah, of course. It's not pathologic.
Yeah, but yeah.
Oh, je regardais pas.
But sorry, I didn't understand this issue with the bound states. Can you explain to me? Because my main way of thinking is that you have bands, then the bands refer to the continuum. You choose your spectrum is such. Of course, it means that you only have a very specific set of conditions which are extreme. I think it was not a provision you made. C'est juste que je vais et je lui ai dit, je te dis, je cherche techniquement, c'est exact. Pour faire court, je fais des codes pour calculer des trucs évidents. C'est la réaction comme ça. Et là, je lui ai dit, cette façon de parler à je vois tellement que oui, j'ai dit le nom. Voilà. Et j'ai montré le livre blanc et vert de la théorie statistique d'échange. Alors, ouais, je l'ai pas ouvert, quoi. Voilà. Donc, je vais en partir et est-ce que j'aurais réussi à retomber sur une situation non linéaire en fait? Celui-là. Ah! Celui-là, il est ça. C'est un peu avantagé. Ça n'existe pas. J'avais vu ce moi, je noté des trucs en violet, c'est devant la typo. En bleu, c'est débrouille-toi toi-même. Ah, je sens pas très bien ce qui se passe. C'est un peu. Je serais éternellement surpris. We have to publish this.
Yeah, I think so.
I mean,
I need to produce that as well.
you know that.
Yeah, and I'll in the next examples I'll show you. There's examples of this autograph transform where everything is well controlled.
Yes. Yeah. Just check specifically GG and then check the solo, Mercury, some way produce it, that's it.
Short paper this week.
I think I won't manage to finish today as well. I don't think I will manage to finish my lecture today. No, I don't think there will be a part 5.
Just, I know, man.
I must
Put the slides on the website
yeah.
and be done with it.
It could be something like that.
So the exam will be on what? On the holograph transform. Yeah.
I just cannot get out of my mind that Sechharov found all the equations in 1971, and then everyone forgot it for 30 years.
No, it was an approximation of the
It's an approximation. Just with pure intuition.
It's for sale again.
No, but the thing is, it's really counterintuitive that it works like that, right? Because basically the point of the rarefied gas is that solitons will only interact pairwise, and then you're sure that you can write it like that. But then to say that even the dense gas where you have a pile of 10 solitons on top of each other, it's still 2 by 2. It's not it's not obvious.
They found the Soliton gas before the IST of NLS was even discovered.
Yes. Désolé, je viens juste de capter ton message. Should we start again, or should we wait for Ben and transfer? What do you prefer?
It's already.
Yeah.
Ben knows most of it.
Next things it doesn't.
Okay, then it's up to you.
But no, it's fine. I think the very beginning would be okay. Okay. So yeah, as I told you earlier, this next section will be dedicated to illustrations. And that's because the formalism can seem to be a bit daunting at first, and it's not clear a priori why we should use it, what we can do with it. So the next section will be dedicated to two particular cases of the gas. The first one will be polychromatic Soliton gas. So this is not the most physically relevant gas, but it's probably the simplest one you can construct. Okay, so it will serve as a nice toy model. Okay, so here we look at the particular case of Soliton gas where the density of states can be reduced to weighted sum of derived data functions. Okay. So this is an idealization because in KDV you cannot have two solitons with the same spectral parameters. So in practice you need to replace delta by some narrow distribution around eta j. Okay, but this makes sense in the context of the thermodynamic nonlinear dispersion relations or the hydrodynamic equations. Now the other GHD equation under this application they reduce to an n-component system of hydrodynamic type for the propagation of the weights and with effective velocity that are defined in this way. And the main point of doing so is that the theory of a system of hydrodynamic type is very well known, and this type of system in particular have been well studied. So, in particular, it's been shown that for any finite m, there exists m Riemann variance diagonals of the system. And this is non-trivial because during my first, if you recall from my first lecture, I told you that for a system of hydrodynamic type of 3 or more components, in general, the Riemann variants do not exist. So the fact that here they do for any finite m is already some interesting property. Okay. And also this, this is the Riemann variant, and as you can see, it kind of looks like also the equation, like a discrete version of the equation that the K was solving earlier. Okay, and in fact, this is consistent with my previous claim that sigma or n is in fact an analogous Riemann variant of the system. Okay, so here, if you define Rj as sigma of eta j, this eta squared factor can be factored out in the hydrodynamic equation, and everything stays consistent here. So it seems obvious when you are looking at it like that, but it's funny to note that at the time people didn't realize that sigma was a Riemann variant for the system. No. In fact, the first time was mentioned was in our paper. Yeah, so more than 10 years ago. So that's it. Okay. It's also been shown that for any finite n, the system is linearly degenerate and it has the bi-Hamiltonian property. And hence it's integrable via algebraic transform. So these are just a discrete version of the previous relation that I showed you before. And this, everything has been checked with products, you can solve it. Where here's a degrees of freedom, you have n functional degrees of freedom instead of a continuous. Okay. So finally, it's also been shown that for a finite n, the polychromatic projection is also a Liouville integrable Hamiltonian system in the traditional sense that you have n constant quantities that are functionally independent and Poisson can move with each other. With respect to Poisson brackets, that is non-local and a bit complicated to write, so I don't write it because otherwise I would need to introduce some more objects. And this lecture is already heavy enough with definitions, I think. And so that means that we also have reasons to think that in general GHD equation should be an infinite dimensional integrable Hamiltonian system, and like KDV is, but the lax pair of no good. Okay. So as you can see, even in this simplest case of the polychromatic gas, solving the general n component system can be pretty involved. So to conclude this section on polychromatic gas, I'll discuss the simplest non-trivial case, which is the two-component Riemann problem.
Sorry,
Yes. Yes.
The equation are m, right?
Yes, you have m equations like that. Okay, so the Riemann problem, which is also known as the partition protocol or the short-tube problem, it's a standard problem in hydrodynamic theories, and it's usually used as a benchmark to evaluate the validity of an approximation or the accuracy of a numerical scheme. And it corresponds to an initial value problem where you have a piecewise constant initial condition with a discontinuity at x equals 0. Here, and here I will focus on the two-component Riemann problems that we can solve explicitly without even having to resort to the other transform. So here maybe I'll go a bit faster than I was expecting to because I think I'm getting too much. But yeah, so the main idea is you start by looking at this equation. You see that the x and t dependence of the velocity only enters through the weights. And for the case of two components, you can exactly solve this system of equations and express explicitly the velocity in terms of the weight where phi is the phase shift. Then, because the equation and the initial condition are invariant under this rescaling, you know that the solution should be self-similar. Because it's linear degenerate, there can be no shocks. Okay, so the only self-similar solution that can be acceptable is piecewise constant and separated by propagating contact discontinuities. The question is how to get those the velocity of those contact discontinuities. To do so, you impose that you must have conservation of the number of sections across the discontinuities. This yields this type of Rankine condition. So this gives you four algebraic equation. You have four unknown. You have CL, CR, and the weights W1C and W2C at the middle. Okay. So this you can solve. I write them here for the measure, but ultimately that's what you get. So you have your initial components on the left and the right, and you have a middle part that expands with velocity CL on the left and CR on the right. The second particular class of Soliton gases I want to discuss today is the so-called Soliton condensate, and it's defined through the NDR as the limit sigma goes to 0. So in a way, you can think of this as a regime in which the interactions are dominant. Okay? And this also corresponds to the densest possible gas for a given support gamma. So that's something you can already see from here, because all the terms, the kernel, density of state, sigma, and each are definitely positive definite. The sigma is the ratio of the bands and the gaps, but it's also 1 over the occupation function. Okay. So the densest gas transportation you can also see from there, because in the limit sigma goes to 0 and goes to infinity. Okay, so you are putting all your solutons at the same point synthetically. Then interaction kick in, they repel each other effectively, and you end up with a final density, which is maximum. Okay. So I'll tell you a little bit about that later. Okay. So first, let me show you how to compute the density of states of a genus N condensate. So what I mean by genus N condensate is a condensate associated with N gap, spectral support gap. And so here I'll be focusing on the first nonlinear dispersion relation because solving it, the method I will solve it can be straightforward adapted to the system. And here, existence and uniqueness of the solution of the general MDRs, it was proven in 2021 by Colliers and Torvis, as well as the positivity of rho. I won't go into the details here. I will just show you how to solve this. Okay. So the first thing I will do to solve it is start by performing the whole continuation of the density of states to minus n. This is to put my equation in this form. And to get then the canonical form of the MDR, I need also to perform take the derivative. And this is nice because it rephrases my condensate nonlinear dispersion relation in terms of a finite Hilbert transform. And this I know good note. Okay. And if I want to do the same thing for the spectral flux, I will end up with also the same kind of equation. Instead of 1, here will be, that would be 12 meters. So, same thing, I need to invert or invert transform. So, without going into details here, this is the general form the density of states will take for n gap potential. So, here you have a ratio of a monomial of degree 2n plus 1. If you want to have the free energy flux, this would be a degree 2n plus 3. Okay. And here you have the radical of the Riemann surface associated with the spectral support. Okay. And P here has only real coefficients, and you can find those coefficients through this normalization condition over the gaps. Right? So what you need to do is solve those 2n equations, right? And these are only one solution, and then you have completely specified the density of states. So in general, this can be a bit tricky to do, right? It's made easier by the fact that this also implies that the zeros of the polynomial P are all within the gap. So you have 1 0 per gap. So this helps. In general, it can be a bit complicated to do. But for example, here with the genus 0 density of state, which is rather simple, you can see it's just the derivative of the circle. And here is genus 1. You see that already things get a bit more complicated because here it involves a ratio of complete elliptic integral. So already genus 1 is pretty complicated, but we know in general to solve this. Okay. So now that we have the density of states of our condensate, we can use it to compute the averages of the conserved charges. Okay. So recall that here the average are defined as the amount of charge carried by a single Soliton. For KDV, takes this as a single form, integrated over the density of states. And for the genus 0 condensate, you end up with this rather compact form. Okay. So, as I said last time, it's not clear how to relate the average of the conserved densities to the statistical properties of the field in general. Presumably, if we have the density of states, we should be able to to have everything you want to know about the field. But in practice, since you have these nonlinear interactions, we don't really know how to do so. But interestingly enough, the first two charges give us directly the first two moments. So those are the most important. And for the zero condensation, you see that's something interesting here, because you see the first charge is proportional to the field, the second charge is proportional to the field square, and here you can see that the average of the field, the average of the field square is just the square of the average of the field, which means that at the genus zero condensate, the variance is zero, which implies that the solution is almost surely constant. And even though that you have inside of the stochastic nature of the certain gas. Okay, so you have essentially only one realization, which is the constant. Okay, and what I mean by that is that if I generate n Soliton solution with parameters that are distributed according to the genus zero density of states, that's what I end up with. So here you have 150 Soliton solution. Here, because you have some finite size effects on the side, which are reminiscent of the Gibbs phenomenon, but you can see that on the bottom, you closely approach the constant. Okay. And that's what you get also if you focus on the bottom. So here's 100 and 200 Soliton solution compared to the constant background, and here on the right you have absolute area for 50, 100, and 200 Soliton solution, and thankfully you see that's because down with the number of Soliton. So this has also been studied more rigorously, but I won't go into that today. Okay. So here, in fact, as I said, for the genus zero condensate, in the thermodynamic limit, you are almost surely constant. There's only one possible realization. So this is a zero entropy state, essentially. Okay. And in general, the condensate corresponds to the lowest entropy state for a given spot. So genus 1 won't have zero entropy, but it's the lowest entropy you can get from this kind of gas.
This one would have one free parameter.
Yes, which is the initial phase. But another interesting aspect with the condensate here is that if you recall during my second lecture, I told you that if you're considering a band gap spectrum that involves only one solution band, then the associated solution to KdV is a constant. So here we have also a band constant. So people, in fact, when people started to look at genus 10 condensate, and they realize Soliton solution by distributing them according to the genus 1 condensate density of states, they found out something that looked similar. In fact, here in red you have a nodal wave that is on top of genus 1 and Soliton solution, 200 Soliton solution with parameters distributed according to genus 1 condensates. And on the right, you have the same thing as before. You have this error for 50, 100, and 200. The same thing. If you generate a Soliton condensate of genus 2, you will have a two-phase solution to KdV. Okay. So.
So it's a colloidal wave on the background?
No, it's just a colloidal wave. Yeah. It's just a colloidal wave. That's fine. Okay. So again, this is no proof, but it lends a bit more credence to what I was saying earlier. Is that you can take a solution with continuous spectrum, you can approximate it by populating densely Okay, but now given that the condensate is just an n-phase solution, you can ask yourself what's the point of doing all this, okay? Because the n-phase solutions are well known. We know how to write the field associated with n-phase solution explicitly, whereas here with this Soliton gas formalism, we presumably only have access to the first two moments. So why are we doing this?
Yeah.
Yes.
So in the certain gas, you have more information than the phase solution. I mean, you have the density on the support. Right?
Yes.
It's not a real function.
Yes.
Does it have a meaning in the phase solution?
No, because you just have a continuous support.
So why would it?
So okay, so the density of states here, you need to pick your the spectral parameters of your solitons in a very particular way, so that to construct the densest gas possible. Because depending on the spectral parameters of the solitons, the phase shift can be more or less large. So you want the right distribution so that it's the densest. If you put a different distribution of spectral points, you will have something that is more diluted. Does that answer your question?
Yeah. I just wondering. So it had no meaning in the phase solution itself. You wouldn't have found this solution, just this form of rho, just by looking at the end phase solution.
Yeah.
To be the connection to certain.
Yes. But there are also other reasons to look at this kind of the objects. And the first thing the most important one is probably the fact that you can use this and Soliton condensate as backgrounds. Okay, and you can put Soliton or Soliton gas on top of it. And for example, this is something that people are currently doing. They are looking at what happens if you put an Soliton solution on a cloudal wave. So there's a very recent paper by Bertola Jenkins and all this from last year. This is another paper by Girotti, Gemma Claflin, Jenkins also, where they do the same thing for modified KDV. So that's a rather complicated problem. And here you have a formalism where you can put everything in the context of one framework, which is the Soliton gas. Okay? So you treat your background as Soliton gas, you put a Soliton gas into it, so you know how they should interact and what should be the hydrodynamics. So that's probably the main thing. Yeah. But I will give you more reasons why to study something condensate. But in order to do so, I first need to talk about the modulation of Soliton condensate and what the dynamics look like. So first, let me recall the GHD equations for the KDV gas in general. So here we will be dealing with condensate, so we're dealing with initial conditions which can locally be approximated by a condensate with sigma is equal to 0. So, but the thing is, as I told you earlier, so condensate is a zero entropy state, and at the Euler scale, there's no entropic reduction, it's merely transported. So that means that if you start with a condensate, you will remain at condensation. Okay? We still have sigma 0 all the time. And so given that, because of the nominal dispersion relation, we expect that the density of states, its functional dependence on eta should remain the same at all times. So we should ask ourselves what changes under these dynamics. Okay. And also, because sigma is 0 everywhere, you see that a priori we shouldn't have any Riemann invariant representations. We need to find a way to solve this equation without that. Okay, so if okay, so to think about what should change here, we can look at the simple example of the genus zero condensate. So as I told you earlier, the genus zero condensate was actually constant, meaning that the modulated condensate should just be a long wave. Okay. And as before, I told you that the value of the constant field associated with the genus zero condensate was just the square of the endpoint of the band. So here, what we are doing is, with modulation, is just putting modulation on the endpoint of the band. And ultimately, what we have is that this PhD equation, condensations, morph into a set of equations for the endpoints of the spectral support. And that kind of makes sense, right? Because if you have your modulated condensate like that, if you look at this fluid cell, let's say, and you, for simplicity, I isolate it from the left, then this construction, we expect that on average, the fastest Soliton will leave this cell earlier than the other. And KV also is to the right, and to the right with velocity that increases with spectral parameters. So that means that after a certain time, the maximal value of the spectral parameter Soliton can take within this fluid cell will be lower than gamma naught, because the fastest Soliton will have left. And similarly, so effectively your spectral support of this cell is shrinking. Similarly, this cell will welcome the fastest Solitons, so its spectral support will expand. So the hydrodynamics morphs into the hydrodynamic equations of the endpoints. So we, ultimately, what we get is a system of hydrodynamic type for modulated GSA condensate. And now, in fact, as you can see, V is outside of the X derivative. So instead of in the absence of sigma, it's the endpoint that plays the role of the remaining value for the system. So we keep this kind of structure, which is pretty nice. And the characteristic velocities are obtained in terms of the effective velocity at these endpoints. Okay. So you can show also that this system has semi-atomic properties, so it's still yes.
But just one question, and so essentially, what you have in this case is very similar to these evolving Fermis.
Exactly.
And the question is, if I add Soliton on top of the condensate, cannot you use the quantum GHB formalism, like small fluctuations, the evolving Fermis, which are just linearized sound waves on something?
Yeah, I don't know about that.
Well, I mean, it makes no sense, but
quantum GG assumes some distribution, some correlation.
Whatever you put on top of a condensate, isn't it too obvious that you can almost always approximate them as small Gaussian fluctuations? So this is essentially a Rattinger like this. Maybe. Yeah.
I don't know about that, so it's interesting.
But thanks for confirming this picture. I didn't hear. Okay. So
yeah.
This is what.
Yeah. So it's not exactly the same.
Okay.
Question? So again, this system keeps the similarity property. It's still solvable by Oliver transform. However, this time, as you can see from there, the system is not linearly degenerating. So it's, in fact, it's generally non-linear, which means that shocks will happen for broad class initial conditions. And in fact, this kind of systems, the shocks get regularized by increasing the genus of the condensate. So in fact, the functional dependence of rho on eta can change, but you can only in a very particular way. So you go from density of states of genus 1 to genus 2 or genus 1 to genus 0 or something like that. Okay. And that's something that we can clear when we look at the Riemann problem. Okay. So here my Riemann problem would be piecewise continuous for the field, which corresponds to genus 0 condensate with different endpoints on the left and the right. Okay. So here I won't write the explicit solution. I will just focus on the phenomenology. Right. But here I need to distinguish between two cases. First case is gamma minus plus, which corresponds to this kind of field. In this case, this component is slower than this component. So the characteristic never cross. There's no shocks. That's something you can see also from here, where you have the evolution of the support in space. And as before, you have something that is self-similar. You have genus 0 here, the genus 0 here on the left and the right, and in between, you have a genus 0 with gamma that varies, that depends on exponent. And that produces a rarefaction wave in terms of the fields that I will show you a bit later. The other case is gamma minus is bigger than gamma plus. So this time the velocity of this component is bigger than that one. So there's a shock at t equals 0. There's wave breaking. And as you can see here from the support, you start increasing the genus of the solution. The shock. Okay. So again, on the far left and the far right, you have genus 0, and in between you have a genus 1 within a region that extends this time. So in terms of the wave field, that's what it looks like. So you start with a genus 0, say on the left and the right, that you here approximated using an n solution, and if you go into each similarly, if I take the opposite way, okay, you have genus 0 here, and this will decompose into a dispersive shock wave, which is a modulated genus 1 solution. Okay. As I told you earlier, from the density of states, we cannot really reconstruct exactly all the statistical properties of the field for now, but we know how to compute the first components. And so here in red, we have anticipation, in black, we have the theory, and the secret very well. Okay. Here's the same thing where you start with the genus 0 and genus 1, which then produces a generalized rarefaction wave. In the opposite, and this is a generalized statistical wave. Again, this works very well. Okay. So once we got here, we can ask ourselves once again what's the point of all that, because so n-phase solution and the modulation as well are well known. Okay, so here again, this can seem as a very roundabout way of doing things, but again, there are some reasons to use this kind of formalism. And the first one is that this Soliton picture gives us a clear understanding, a clear phenomenological understanding as to why the genus, the solution, should increase the shock, which is not as clear when you are looking at the n-phase solution. And again, I think the most interesting thing with that is that you can use those related condensate as backgrounds, because if putting an Soliton solution on an n-phase background is complicated, putting it on a modulated n-phase is even harder. Okay, so here you have something that's really nice. And if you want a concrete example of this kind of thing, you can look at something that people found out by using this kind of formalism, is that you take a reflection wave, then you can send solitons from the left, and then depending on the spectral parameter of the solution, it will either get stuck within the reflection wave because its velocity is not large enough, or it would be able to tunnel through it. And just like that, you effectively build a nonlinear field. This is a very interesting proof. So I'd like to talk about this a little bit more. But, in fact, this kind of result has not been published yet, even though they will be soon. That's not to say. Sneak peek. Right. Okay. Right. Now I will briefly mention one last thing, one last motivation for studying condensate, and this lies in what's called as the diluted condensate, which is defined through its density of state by taking the genus M density of state in condensate and multiplying it by the dilution constant, kappa, which is smaller. So that's what it looks like for the genus 0. Then we can plug this into the non-linear dispersion equation. Then we have sigma. From sigma, we can get the spectral flux using the second NDR. We can get the effective velocity, etc. So I don't write everything, but we know how to compute all the main objects in this situation. Because the diluted condensate is so close to the actual condensate. And that's what it looks like for the field for genus 0 diluted condensate for dilution constant, which is 0.97. And here on the right, you have the evolution of the variance of the diluted condensate with respect to the dilution constant. So you start with a condensate of variance 0, you dilute it a bit, you increase the variance. That's because you allow it and you give it more space to roam and interact in more different ways. And then you hit maximum. You start decreasing with the dilution, and that because solitons become the gas become too rarefied, so solitons don't interact as much. And here, so most of the randomness comes from the non-linear interaction between solitons. Okay, so a genus N diluted condensate is essentially an incoherent N-phase solution. So the phenomenology that you have here is pretty rich, and it describes things that were previously completely out of reach. And you can ask about the physical relevance of this kind of thing, but I think at least when it comes to the genus 0 diluted condensate, modulated or not, it should be pretty relevant, because what you are dealing with is essentially a long wave with a random perturbation on top of it, which is kind of natural to consider.
No, with a very special type.
Yeah, of course. Yeah. And that's also something that needs to be studied, is what kind of fluctuations you're putting in terms of the field when you dilute your condensate. Yeah, so this is also an example of a different problem. So you have incoherent velocity wave, incoherent rarefaction wave. Okay, so probably that I will stop here, and I won't talk about the extensions of DHT because there's another lecture. So yeah, right. So yeah. Yeah, it will be too long, I think. No, maybe a few things I can say very quickly is okay. We can have more information with GHT. We can We can have more correlations. We can add some diffusion or dispersion to the GH equation. We can add some forces, effective acceleration, stuff like that. But also there are some other interesting models to study. So there's focusing NLS. So here you have two sets of nonlinear dispersion relations. So it would be interesting to understand. Boussinesque, I won't talk about, except that here, if you look at Boussinesque, you have some quirks like the possibility of Soliton's merging. So if you look at the asymptotic state, we don't have enough information to reconstruct everything. So that's an interesting thing. You have GHD in 2D with geometry perspective or things like that. And also, the last thing I will talk about is the weakly integrable models that are solvable via inverse transform. But the main thing is here, they have also infinite number of constant quantities, but the set is not complete. The scattering is not totally reducible. So what do we do with the GH equations when this is the case? Right. Thank you.